Hello students, this is another lecture on vectors. In this lecture we are going to take external division section formula. We will take midpoint formula. Then we will take the centroid of a triangle and centroid of a tetrahedron. So we are going to see these formulae in this lecture. So let us begin with external division section formula. External division section formula. In earlier video, we have completed the internal division section formula in detail. Now to start with, let us have a line here. I have a line here, and on this line, I have a segment. The segment is, say, AB. So I have 2 points, A and B, on this line. So the position vector of these 2 points are known to us. Say I have somewhere origin. So from origin, I join this point A. So this vector gives me the position vector of point A. Here I have point O, that is the origin. So this vector, which gives me the position of point A, is known as A bar. And here I have the position vector of point B. This I will call as B bar. Now there is a point on this line segment, and that point is not in between A and B. That point is outside A and B. It is on the line, but here it is. And say that point is R. This point is R. You can take any point. You can take P, you can take C, whatever. What is important is this point is not in between A and B. It is outside A and B. It is this side. This point we could have taken even here. Even you can take it here. So I'm taking it on the right hand side. Now this point R is dividing the segment AB. Here I write the statement. I write here point R divides segment AB externally in the ratio M is to N. Now what does that mean? It means, see, the point of division, which point is dividing? R is dividing. And what segment is it dividing? This is dividing segment AB. See, the order is important. It is R dividing AB. So the ratio of division will be AR upon BR. What will be the ratio of division? It will be AR upon BR. And what have they given? They have given the ratio to be M is to N. So AR upon BR is M upon N. You can write even AR upon RB. That is okay. Even AR upon RB is also okay. Why? Because BR or RB, the length is same. You can write even RA upon RB. This is all done. This is all correct. So it means from here to here, AR, this is M. This is M, and BR is N. This one is N. So if that is the case, then I'll be able to write the position vector of point R. The position vector of point R is this, R bar. This is R bar. So if I have these things given, that is, I'm given the position vector of point A as A bar, position vector of point B as B bar, and I'm given the ratio of division of point R. That is, point R is dividing segment AB externally in the ratio m:n. Then R bar can be found. We can find R bar in terms of A bar and B bar. And what will be R bar? R bar will be equal to MB bar minus NA bar upon M minus N. What will be R bar? R bar will be MB bar minus NA bar upon M minus N. So now we are going to prove it. We will first prove this, and then we will also write the external division section formula for the coordinates of point R. So that will be the second part. Right now, let us do the first part. So what I have to prove here, now I write. So let me write the theorem. Point R divides segment AB externally in the ratio m:n. Then prove that, here I will write the theorem. Prove that R bar equals to MB bar minus NA bar upon M minus N. So let us start with the proof. I will write here, since point R divides, so the proof starts from here. The diagram will come in the proof. Since point R divides segment AB externally in the ratio m:n, therefore we can write, what we can write? AR upon BR. R is dividing AB, so AR upon BR. Okay, this is very important. Whether it is internal section formula or external section formula, you will always take the ratio the way I just showed it to you. AR upon B bar, AR upon B bar, BR equals to M upon N. Remember, everything is numbered. In this, everything is numbered till now. Next step is, I will write therefore NAR equals to MBR. This is also number. Everything is number in this. Now I am going to introduce the vector. Therefore, N AR bar. Now see, I have converted this AR segment into a vector. So now when I am doing it, See how will it look like. AR vector will be this vector. You see this? This is AR vector. This is AR vector. And here I have M and BR bar. I'm writing BR bar. So how is that BR bar vector? BR bar vector is this way. Now you notice that direction of AR bar and BR bar is same. So since the direction of AR bar and BR bar is same, what will happen? What will happen? Here we will write, since the direction is same, MBR bar, and I notice that both have the same direction, what will happen? I will write equal to sign, and I don't have to put any negative here. I don't have to put any negative sign. Okay. But remember, in case if someone had written it the other way, let me do it that way also and show it to you. If someone had written it, as I told you, you could have written AR upon RB equals to M upon N. Then you would get NAR equals to MRB. But when you write vectors here, so NAR bar, and here you have MRB bar. Now look at this. AR bar, if you have written it this way, then AR bar would be this direction, but RB is the opposite direction, RB bar. In that case, before you write equal to, you will put a negative sign because of the opposite directions of vectors, and then equal to sign. So this thing you have to take care of. This thing you have to take care of. In either of the ways, you will get the same answer. You will get the same answer. So the next thing I will do is, as we know, AR bar is R bar minus A bar equals to M. RB bar is R bar minus B bar. So N R bar minus NA bar equals to M R bar minus MB bar. I shift MB bar on the left and NA bar and NR bar on the right. And this one I shift on the right hand side. So I get here, therefore, MB bar minus NA bar equals to MR bar minus NR bar. Taking R bar common, I'll get M minus N here. M minus N is a number. And here I have MB bar minus NA bar. So the final step will be therefore R bar equals to this MB bar minus NA bar divided by this M minus N. M minus N, and this completes the proof. We have obtained what we needed to obtain. So this is what is your proof. I hope you have understood this. You can copy this and do it well. Now I will tell you the techniques to remember the formula. See, here you have point A, point B, and here you got point R. What we will do is the position vector of A and B, we will write beside them. Okay, no need to show the vector. This A bar is nothing but a vector which gives you the position of point A, but you don't have to show it. Just write beside point A. This is A bar, and position vector of R is R bar. What further we know? We know that the ratio of division is M is to N. So from here to here we have M, and this is N. This is N. Now we will write the formula. See how to write the formula. R bar equals to, always remember the formula is written for the point which is dividing. So it is R dividing segment AB. So you will write the formula for R bar. Okay, you will not write the formula for B bar or A bar. It is for R bar you will write. Always the point which is dividing, the formula is written for that. Now see, between R and A, you have M. Between R and A, you have number M. So M will multiply the position vector of point B. So you have MB bar minus because it is external division. Between R and B, you have number N. Between R and B, you have number N. So N will multiply the position vector of point A, which is A bar. So MB bar minus NA bar upon M minus N. See how easy this one is. I hope you followed it. Now we will go ahead and take the formula for the coordinates. Suppose we are given, let A have the coordinates x1, y1 and z1. B has coordinates x2, y2 and z2. R has coordinates, point R has coordinates x, y, z. Now see, when I'm writing x, y, z, it means these coordinates are unknown coordinates. When I write the suffix 1 or 2, like x1, y1, z1, here I have written x2, y2, z2. These are given coordinates. So what I'm given? I'm given point A and B coordinates, and I'm also given the ratio in which point R is dividing segment AB. So if I know all this, I can write the external division section formula for the coordinates. So see, for this what I will do. If point A is this, point A coordinates are these. So I will have therefore A bar equals to x1 I cap plus y1 j cap plus z1 k cap. This has been already done for you. And B bar will be x2 I cap plus y2 j cap plus z2 k cap. And R bar will be x I cap plus y j cap plus z k cap plus z k cap. I substitute these all in the formula here. I substitute A bar, B bar and R bar in the formula. So I write this as 1. This is 1 here. I write using A bar, B bar and R bar in 1, we get, see what we will get. We will get here R bar equals to, what is R bar? X I cap plus Y j cap plus Z k cap equals to M times x2 I cap B bar, M B bar. I'm writing the coordinates of B bar plus y2 j cap plus z2 k cap minus n into A bar, x1 I cap plus y1 j cap plus z1 k cap upon m minus n. So the next step I get therefore xi cap plus yj cap plus zk cap equals to, see, this m will multiply x2 I cap, y2 j cap, z2 k cap. M will multiply these three and n will multiply these three, right? Now when you do that, mx2 I cap minus nx1 I cap, you will take I cap common and you will get mx2 minus nx1 I cap plus my2 minus ny1 j cap plus mz2 minus nz1 k cap. This is what you will get, and here m minus n. Now I will separately divide for these three terms. I will split the denominator. What is the denominator here? This is denominator. I will split the denominator for these three. Okay, that is m minus n will come in the denominator of these three terms, which are in the numerator. So I will get, therefore, xi cap plus yj cap plus zk cap equals to mx2 minus nx1 upon m minus n times I cap plus here inside the bracket I will get my2 minus ny1 upon m minus n j cap, and this will be mz2 minus nz1 upon m minus n times k cap. Now from this you can, now since the left hand side vector is equal to right hand side vector, by equality of vectors the coefficients can be equated. So x is this, y is this, and z is this. So what you will get? You will get, therefore, x equals to mx2 minus nx1 upon m minus n, y equals to my2 minus ny1 upon m minus n, and z is equal to mz2 minus nz1 upon m minus n. This is the complete detail about external division section formula. The next we are taking is midpoint formula. In midpoint formula, what happens is we have 2 points A and B on a line, and there is another point which is M. M happens to be the midpoint of segment AB. Now you know if M is midpoint, then AM will be equal to BM. These two segments will be equal to each other. They'll be equal, and because of that, AM upon BM will be equal to 1. Now this 1 can be written as 1 upon 1, 1 is to 1. So AM upon BM is 1 is to 1. What does that mean? AM upon BM is 1 is to 1. It means point M divides. See, M is being repeated. M is in the numerator and M is also in the denominator. So what you understand is point M is dividing segment AB internally in the ratio 1 is to 1. Okay, so whenever there is a midpoint, the midpoint always divides the segment in the ratio 1 is to 1. That you need to follow. So what will happen is, here I write the statement. Point M is midpoint of segment AB. Okay. Now, if position vector of A is A bar and position vector of B is B bar, then the position vector of point M bar can be given as follows. It can be given as follows. You can apply the internal division section formula, because what is M doing? M is dividing segment AB internally. So here you will apply internal division section formula. Before that, I will write the position vector here, A bar, B bar, and point M has position vector M bar. Now you should know that inside the bracket, I have written A bar, but A bar is a vector that you need to follow. What will be A bar? Somewhere you will have the origin. I'm not drawing it, but from origin it is this vector, which is A bar. From origin you have this vector, which is B bar. And from the origin you have this vector, which is M bar. So you are writing the formula for M bar. If you know these two vectors, you can find out this vector. That is M bar, you can find out. Okay. But remember, you need not be always showing the vectors. It is understood. So here we have, let us apply by internal division section formula. Internal division section formula. What you will have? You will have here M bar equals 2. Now you know 1 multiplies B, the position vector of B, and this 1 will multiply the position vector of point A. So 1 into B bar, that is B bar, plus 1 into A bar, that is A bar, upon 1 plus 1. So what is M bar equal to? Therefore you have M bar equals to A bar plus B bar by 2. This is the formula for position vector of midpoint. Okay, now we will go for the formula. We will go for the formula when we know the coordinates. When we know the coordinates. So here I write, if A is, we will extend this formula for the coordinates. If A is x1, y1, z1, a point in the space, B is x2, y2, z2, another point in the space, and M is, say, unknown point x, y, z in the space, then if I know this and this, if I know these coordinates and I know that M is the midpoint, I can write the coordinates of M. What will be x? X will be simply x1 plus x2 upon 2. Y will be y1 plus y2 upon 2, and z will be z1 plus z2 upon 2. This is the detailed information about midpoint formula. Now the next one is formula for centroid of a triangle. For this, I have a triangle here, point which has the vertices A, B, and C. The position vector of these points are, these are the vertices of the triangle. Point A, B, and C are the vertices of a triangle ABC. The position vectors are A bar, B bar, and C bar. It is needless to say that these A bar, B bar, C bar are the vectors which originate from the origin. You don't have to show that. But remember that these are vectors. A bar, B bar, C bar are the vectors, position vectors. Now here I see three medians. I see three medians of the triangle. So here I have a point here D, which is midpoint of segment BC. When I join A with D, when I join the vertex A with the midpoint D, I will get one median of the triangle. Here I have another point E. So BE is, E is the midpoint of segment AC, and hence BE is another median. And finally, here I have point F, which is midpoint of AB. So CF is the third median. Now these three medians of a triangle are concurrent. They are concurrent, and that is they will intersect at one point. These three segments will intersect at one point, and this point is given by G. So point G is the centroid of the triangle. What is centroid of a triangle? Centroid of a triangle is the point of intersection of medians of the triangle. Okay. And the position vector of point G is G bar. It is G bar. The question here is, if I know the position vectors of point A, B, and C, and G happens to be the centroid of triangle ABC, I can find out the position vector of centroid in terms of the position vector of these vertices. And that is G bar will be equal to A bar plus B bar plus C bar upon 3. This is what we have to prove. What is centroid of a triangle equal to? G bar is A bar plus B bar plus C bar upon 3. Very simple one. Let us do it. So here I write the statement of the theorem. So the statement of the theorem is A bar, B bar, and C bar are the vertices of triangle ABC. G bar is the centroid of triangle ABC. Then prove that G bar is equal to A bar plus B bar plus C bar upon 3. Okay, let's go for the proof. We will prove it here. Now, as you know by geometry, D is the midpoint of segment BC. I write here, since D is, or I'll write here, AD, BE, and CF are the medians of triangle ABC. Point G is point of intersection of these medians. Okay, by geometry we know that this point G, which is the centroid, it will divide the segments. It will divide the segment, that is median AD. It will divide median AD in the ratio 2:1. From the vertex, it is 2 sections, and from the base, it is 1. So it is 2:1. Point G will divide AD internally, definitely internally, in the ratio 2:1. Further, point G will divide segment BE again in the ratio 2:1. From the vertex B, it is 2, and from the base AC, it is 1. And here, for CF also, it will divide in the ratio 2:1. Okay, so ahead we go, and I write by geometry, point G divides segment AD or median AD internally in the ratio 2:1. See, I wrote AD. That is why I'm writing 2:1. If I had written DA, if I had written segment DA, then I would have written 1:2. So please take care of the order in which you select the segment. So point G divides segment AD internally in the ratio 2:1. Okay, I write here, let D bar be the position vector of point D. Therefore, by midpoint formula. See, first I will apply midpoint formula. By midpoint formula, point D is midpoint of segment BC. You see this? Point D is midpoint of segment BC. So what is D bar equal to? D bar will be equal to B bar plus C bar upon 2. Just now we did the midpoint formula. So D bar is B bar plus C bar upon 2. Then I will apply, see, I have got d bar. I have got d bar. What is d bar equal to? The position vector of point D is b bar plus c bar upon 2. Now I will apply the section formula. I will apply the section formula for segment AD. For segment AD, I will write here by section formula, by section formula, see, G bar equals to G bar. Point G is dividing, look at this, G is dividing segment AD. Okay, I'll do one thing. I'll write here by section formula on segment AD. I'm applying section formula on segment AD. So look at this AD. I want you all to focus on AD. Please focus on AD here, AD, right? Okay. So this is what you have to focus on, AD. Now here what you notice, G divides AD in the ratio 2:1. So what will happen? The number between G and A is 2. The number between G and A is 2. The number between G and D is 1. So this 2 will multiply the position vector of D, and 1 will multiply the position vector of A, right? So you will get here G bar equals to, G bar equals to 2D bar, 2D bar plus 1A bar, 1A bar is A bar upon 2 plus 1. So the next step will be, now see, I will substitute for D bar. What is D bar? D bar is B bar plus C bar by 2. So therefore, G bar equals to 2 times B bar plus C bar upon 2 plus A bar upon denominator. I had 2 plus 1. So 2 plus 1 is 3. In the next step, this 2 will cancel this 2, and I will get therefore G bar equals to B bar plus C bar plus A bar upon 3. That is, G bar is A bar plus B bar plus C bar upon 3. This is the formula that we had to prove, and we proved it. I hope you followed it. That is the centroid formula for a triangle. Now we will extend this formula for the coordinates of the centroid. That is, if I'm given coordinates of point A as x1, y1, z1, point B as x2, y2, z2, and coordinates of point C as x3, y3, and z3, then the coordinates of centroid can be obtained. Okay, so let us do that. I write here, if A is x1, y1, z1, B is x2, y2, z2, C is x3, y3, z3, and G is x, y, z. X, y, z means they are unknown. Then we can write the coordinates of centroid. See, I'm not doing the complete derivation. I will directly write the formula. If you want to do the complete derivation, then what you will have to do? You will have to write what A bar is, what B bar is, what C bar is, what G bar is, then substitute here. Then take I cap common, J cap common, K cap common, and then split the denominator 3 for each one of the term. You will have 3 terms in the numerator that can be obtained. So I'm going to give you the direct result, what it will be. So x will be, you will get x, which is the x coordinate of centroid. X will be x1 plus x2 plus x3 upon 3. Y will be y1 plus y2 plus y3 upon 3, and the z coordinate of centroid will be Z1 plus Z2 plus Z3 upon 3. This completes the detailed explanation about the centroid of a triangle. The next we are going to take is the formula for centroid of a tetrahedron after this. So the next part here is formula for centroid of a tetrahedron. In order to explain this, I have drawn here two figures. See, what is a tetrahedron? A tetrahedron is a solid figure and it has got four triangles. So look at this particular diagram first. Now in this you understand that there you see there are four triangles, and because of these four triangles there are four vertices of the tetrahedron that you get. So here A, B, C, D. I want you all to focus on this diagram first and then we will go for this diagram. Okay, so first let us understand what is a tetrahedron. So in a tetrahedron, I have four triangles. See here. So the four surfaces are triangles. So here I have one surface. It is triangle ADC. This is triangle ADC, which you see from this side. This is triangle ADC, which you see from this side. This side you see triangle ADC. Then you have another triangle here, which is the front triangle, and that is triangle ABC. You can check here, triangle ABC is this. This is triangle ABC. Then, so you have these two triangles. Then the another triangle is the base triangle, and that triangle is triangle BCD. That is the base triangle. That is the triangle on which the tetrahedron is resting. It is resting, so it is from down. You know, from down you have triangle BCD. The triangle BCD is a triangle which is the base triangle. And here ABC is a triangle which you see from this side. From this side you see the triangle ABC. This is triangle ABC. And the final triangle is triangle ABD. The triangle ABD you will see from this side, triangle ABD. So there are four triangles you have here. Okay. The centroid of tetrahedron. Centroid of a tetrahedron is nothing but the point of intersection of the segments joining the vertex of the tetrahedron with the centroid of opposite triangle. With the centroid of opposite triangle. So what I'm trying to tell you is, see, look at the triangle, look at the triangle ADC. Look at the triangle ADC. So in this triangle ADC, definitely you will have somewhere centroid. I'm talking about the centroid of the triangle. So see, ADC has suppose triangle centroid here. So what is the opposite vertex of triangle ADC? The opposite vertex is B. Now you join this point B with the centroid of opposite triangle. So see here, this is the segment you get. You get this one. You understand? You get this segment. So when you join, you will get this. Okay, so this is one segment. It is joining the centroid of the opposite triangle from the opposite vertex. Then same way I will have a vertex. I will have a centroid here. See, look at the triangle BCD, which is the base triangle. So that base triangle will also have somewhere centroid. The triangle will have its centroid. Now join this centroid with the opposite vertex. The opposite vertex is this. See here. Okay. Then you have the triangle. Then you have the triangle ABC. You have the triangle ABC. ABC. ABC will have centroid somewhere here. It will have the centroid somewhere here. Okay. And what you need to do is you will join this centroid with the opposite vertex. The opposite vertex is D. You will join this with the opposite vertex, which is D. Okay, here it is. I'll have to shift the centroid a bit. So see, somewhere here the centroid of ABC will come. Okay, and finally we have the triangle ABD. ABD will have somewhere here centroid. Its centroid will be somewhere here, and that I will join with the opposite vertex, which is C. So when I join with opposite vertex C, I will get here. This way it will come. So in this tetrahedron, this is a tetrahedron which has got four surfaces as four triangles. Each triangle has its centroid. When you join the centroid of each triangle with the opposite vertex of the tetrahedron, these four segments are concurrent. They meet at one point, and this point is the centroid of the tetrahedron. It is the centroid of the tetrahedron. And it is believed that centroid of the tetrahedron is the center of mass of the tetrahedron. So if I'm writing this as, say, if I write this as G, so G becomes the centroid of the tetrahedron, and it can be considered as the center of mass of tetrahedron. Further, this centroid, suppose if I write this as this centroid of the triangle, if I'm writing it as G2, if I'm writing the centroid as G2 here, G2, then the centroid will divide segment BG2 in the ratio 3:1. That is, G to B is 3 and G to G2 is 1. Okay. Same way, if this centroid is, say, if this one is, say, G1, so G will divide A G1 in the ratio 3:1. So A to G is 3 and G to G1 is 1. Same way here, if I consider this to be G3, centroid G3, so C G3 will be divided internally in the ratio 3:1. So this C to G is 3 and G to G3 is 1. And finally, if I call this as G4, then G will divide DG4 in the ratio 3:1. Okay. So as such, the derivation is not important. The derivation is not important. I have showed you this particular diagram in order to make you understand it well. So this diagram is drawn here once again. See here, you have four triangles. You have four triangles, ADC, BDC, ABC, and ABD. Okay, and what you are doing is you are joining the centroid of each triangle with the opposite vertices. These all intersect each other at one point, and this point happens to be the centroid of the tetrahedron. It is the centroid of the tetrahedron. Okay, now we are going for the formula of centroid of tetrahedron. I will remove this diagram. One diagram is enough. Okay, what you need to understand here is that for the centroid formula of tetrahedron, the derivation is not important. We will see the statement. See, the derivation could be done, but it is not required, so it will not be done here. We have to get the formula for the centroid of the tetrahedron. So look at the statement. The statement is if A bar, B bar, C bar, and D bar, okay, are the vertices of a tetrahedron ABCD, which you see in the figure. So see here, ABCD are the A, B, C, D are the vertices of the tetrahedron, and they have their position vectors as point A has position vector A bar. It has the position vector A bar. Point B has position vector B bar. C has position vector C bar, and the vertex D has position vector D bar. Point G, which is the centroid of the tetrahedron, it has the position vector as G bar. Then we can write the formula for centroid of the tetrahedron, that is G bar, as we can write it as G bar is simply sum of all the position vectors A bar plus B bar plus C bar plus D bar upon 4. Okay, very simple formula. Like in the centroid of a triangle, what did you do? You added all the, in centroid of triangle, what you did? You added all the position vectors and divided by 3. In centroid of tetrahedron, what you will do? You will add all the vertices position vectors and divide by 4. And divide by 4. Similarly, if you are asked the coordinates, like if you are given the coordinates of point A, B, C, and D, all in X, Y, Z coordinates, like A is X1, Y1, Z1, B is X2, Y2, Z2, C is X3, Y2, Y3, Z3, and D is X4, Y4, Z4. So you can find out the centroid coordinates. You can find out the coordinates of the centroid of the tetrahedron. And what will be the x coordinate? The x coordinate of centroid will be x1 plus y1, sorry, x1 plus x2 plus x3 plus x4 upon 4. Similarly, the y coordinate of the centroid will be y equals to y1 plus y2 plus y3 plus y4 upon 4. And the z coordinate of centroid of tetrahedron will be z1 plus z2 plus z3 plus z4 upon 4, where you know what are x1, x2, y1, x1, y1, z1, what are x2, y2, z2, x3, y3, z3, and x4, y4, z4 are. Okay, so this is the complete detail about the formula for the centroid of tetrahedron. Now we are well equipped to start with the problems, and we will take the problems in the next video. Thank you.